All right, so now we'll move on to Venus. So we're continuing the sort of tour of the solar system that we're doing now. And moving out to Venus is a very significant leap for us from Mercury, because Venus is now the closest thing that Earth has to a twin planet in our solar system. And yet looking at Venus and looking at its properties, other than its mass and radius, it's absolutely nothing like Earth, despite the fact that it's a near twin in terms of mass and radius. So if we look at Venus, we actually see through telescopes a yellowish shrouded surface like this, very featureless. This is actually a topographical map made by mapping the surface using radio waves from orbit. So it doesn't look like this unless we're using radio waves to use topological feature mapping, but it looked at this hazy yellowish object. So what we're seeing here is Venus in ultraviolet rays. And ultraviolet is showing us some features in the cloud tops that are related to composition and properties of the atmosphere. But it doesn't look anything like Earth. And we'll see that even under the atmosphere, it still doesn't look anything like Earth. But we can't see the surface from Earth because of the atmosphere. Okay, so we're moving out away from the sun a little farther now. Now Mercury, at only 40% of an astronomical unit, we've already seen, reaches a maximum temperature of over 600 kelvins. Right? Now the maximum temperature on Earth is a little over maybe 350 kelvins or something like that. So that's Mercury. Now as we move out to Venus, Venus is almost 3/4 of an astronomical unit out. So you might think that Venus is starting to get into the habitable zone, because it's pretty comparable distance to Earth. It's 3/4 of Earth's distance out from the sun. But as we'll see, Venus is not in the habitable zone. It's much, much too hot. And then looking ahead to Mars at 1.5 astronomical units, it's just 50% farther out from the sun than we are, and yet Mars is too far out. It's also not in the habitable zone. So Earth is the only planet in our solar system that's actually in the habitable zone. Now, if we look at mass and radius here, if you look at radius, it's 95% of Earth's radius. Closest we have to a twin planet, it's about 90% of Earth's mass. The density figure on the right is almost the same, just about the same. Typical type of terrestrial density indicating the presence of probably a very dense iron core. And we also see, this is a topographical feature that shows kind of things that are sort of melting on Venus. It always looks like a sort of a drone flying over a pineapple pizza, Domino's or something like that. They use drones for everything now, even pizza reconnaissance. And so it probably looks a little like this. But we also see features that indicate that there have been tectonic processes on Venus in the past, because we see, for instance, these cracks that seem to indicate that this was a lava dome at one point, which probably cooled off and settled and led to cracking. We'll see that there's no evidence for any kind of plate tectonics on Venus. There's no plate motions. There's really no continental features at all. There's certainly no oceans on Venus. So Venus seems to never have really been able to fully participate in a kind of plate tectonic phenomenon that we see on Earth. And yet there is geological activity. There's evidence for volcanic activity. Now Venus being close to the sun is another object which we need to observe either just after the sun sets or just before the sun rises. In fact, Venus is very bright in the sky these days, except the sun set. So just as with Mercury, we can ask, how much time would we actually have to observe Venus? And this comes down, again, to a pretty simple little calculation where we form a trusty right triangle. We have a right angle right there. So I should do this? Yeah. There's a right angle there. And the reason that this is a right triangle is because we're putting Venus where it needs to be to maximize this angle. And this angle is the angle we perceive between the sun and Venus. So we're trying to maximize that angle because we're asking how far in angular terms could Venus ever get from the sun? Because if we maximize that angle, that's going to correspond to the maximum amount of time we'll have to observe Venus either before the sun rises or after the sun sets. Just the same thing that we did in the case of Mercury, but the answer is a little bit different because, of course, Venus is farther out from the sun. So the angle here is about 47 degrees. That's what we call the maximum elongation angle for Venus, about 47 degrees. All right, so Venus with a practically circular orbit, we don't really have to worry about any eccentricity, which we thought about in the case of Mercury. So, how many hours would we have to observe Venus? Well, the diurnal motion, of course, occurs at the rate of about 360 degrees per 24 hours. That's just the Earth spinning. So, the diurnal motion of things rising in the east and setting in the west occurs at the rate of 15 degrees per hour. So if we can have a maximum angle between Venus and the Sun is about 47 degrees, and we think of them as a kind of composite object that's separated by 47 degrees, so if the Sun sets, we'll have as much time as it takes for the diurnal motion to sweep through that 47 degrees. That'll be the amount of time we have to observe Venus. So we do the math, and we divide 47 by 15, and we get about 3 hours. Now, if you remember, in the case of Mercury, the answer was about 2 hours, and that was because Mercury's maximum elongation angle is only 28 degrees, because Mercury is closer to the Sun. So we get about 2 hours to observe Mercury at maximum, and we have about 3 hours to observe Venus. Again, it could be either before the Sun sets or after the Sun sets or before the Sun rises. All right, the albedo for the Moon and Mercury we found to be very low, only about 0.1. They're almost coal-like in their grayness, with an albedo of only 0.1. They're not quite coal black. That would be sort of an albedo of 0, like that. So they're gray. Now, if we look at the Earth with the bright oceans and cloud tops, we have an albedo of about 0.4. For Venus, it's 0.7. So Venus is actually the shiniest object in the solar system, with the exception of maybe a couple of small icy moons, since ice is very shiny. So Venus is actually the third brightest object after the Moon and the Sun. And the reason, of course, it's so bright is 3 different effects here. One is that it is still quite close to the Sun, so it's close to the source of light. And it's also highly reflective with this large albedo, and it's also pretty large. It's about the size of the Earth. So it's much brighter than Mercury, even though Mercury is closer to the Sun. And that's simply because in the case of Venus, even though it's farther away from the Sun than Mercury is, that's compensated for by the fact that it's larger and has a higher albedo. So Venus is really very bright in the sky right now from sunset. Now, as we saw when we talked about Galileo's observations, Venus does go through phases, a cycle of phases, as viewed from the Earth. And we can ask, when is actually the time that Venus appears brightest? Well, it's possible to have Venus right between the Earth and the Sun. This is called a conjunction. It's called an inferior conjunction because it's closer to the Sun than the Earth is. But although this is the time when Venus is closest to the Earth, it's not a good time to observe Venus because the phase that you're going to see is a new Venus. You're going to look at the dark side of Venus. So, of course, even though Venus is closest to the Earth, that inferior conjunction, it's not brightest. In fact, it's darkest because you're just looking at the dark side of Venus at that point. Now, if we move out to the point where we actually see the full half phase of Venus over here, quarter Venus, we would call that. This is the greatest elongation angle because we get the right angle there. So we're seeing half lit, half dark Venus. You might think that that would be the maximum brightness because we're seeing as much of the bright side of Venus as we can see. But that turns out not to be true either because it's a little farther away. So the actual brightest phase of Venus is just simply between those two. It's sort of an 8th phase of Venus between the inferior conjunction and the greatest elongation, because there you get kind of a compromise. It's still pretty close, not too far away, and you're still seeing quite a lot of the bright side of Venus. So that actually occurs at an elongation angle of about 39 degrees. That's when Venus actually appears brightest. And at this 39-degree angle, we see, like I said, almost a quarter Venus, but not quite. Because of the fact that it's actually not at the elongation. The maximum elongation angles, and you're going to see actually a half lit, half dark Venus. Okay, so transits. We know what transits are. We talked about this. This is just when a planet appears to move in front of its star. So it depends on where you're looking at from. You can see a transit of a planet around its star at any time at all if you happen to be in the right spot in that solar system, right? I mean, it's just a perspective thing. So if you put yourself in the right position, you can see a transit of Venus anytime you want to. You have to float out in space to see it. On Earth, the last time that we actually saw a transit of Venus was in June of 2012. And so this was only about a little over a year ago. And I actually knew that this was going to happen, so I set up a little telescope in the driveway. And since we're looking at the sun here, I set up a little projection screen system, because of course, obviously, I'm not going to look into the eyepiece. I mean, we're looking at the sun here, after all. We're looking at Venus moving across the sun, so you're not going to look at an eyepiece to see that if you ever want to see anything again in your natural life. But this occurs every 100 years, so this was kind of worth doing. And so I was able to get a projection. That's a projection of the sun on the screen at the end of that device there. And then you can actually, for some reason, oh yeah, it clouded up. It clouded up right after the event began. So this is the last photo I got. But you can actually see Venus just starting to enter in there, which is part of its march that took place. Just entering in, and it actually was kind of cool to see that little black dot moving in there. That was actually Venus doing its thing. And what happened was it actually made sort of a little arc across the face of the sun. It didn't go straight across like that transit I'm indicating there. It was a little more of an in and out kind of arc thing. Let's see if this is going to work. I think it's even more important to go out and vote, because then you're really honoring the veterans who gave up their lives to protect that very freedom that we have guaranteed by the Constitution. So it really is important to go out and do that. Okay, now, having said that, we simply must start working. Let's see. Restart this thing here. Even went through my patriotic spiel. Yeah. Okay. Ah, that's what's happening. So, okay, let's get that. All right, talking about the orbit of Venus. We enjoy talking about orbits because this is astronomy class after all. And so we have quite a circular orbit in the case of Venus. Its semi-major axis, as we saw, is about 0.72 astronomical units. Not too much eccentricity, and what we like to do is be aware of the relationship between the period and the semi-major axis. I write this down every time we talk about an object orbiting the sun, because it has this uncanny ability to give us the semi-major axis if we know the period, or work in the opposite direction. So here, we take the semi-major axis as known, 0.72 astronomical units. So what we do is we use Kepler's third law to solve for the period of the orbit in Earth years. And to do that, we, as usual, take the square root of both sides, so this 3 power becomes a 3 halves power, which is 1.5. And if we plug in 0.72 for the semi-major axis, we get 0.611 Earth years. So the length of the year on Venus is about 61% of Earth's year. So that's up from about 25% of Earth's year in the case of Mercury. About 225 Earth days. Okay, both properties. Well, we've already seen the density is close to Earth's density, but let's go ahead and remind ourselves how this is actually computed. We take the radius, about 95% of Earth's radius, and the mass, about 82% of Earth's mass. And if we take these values and actually plug them into our standard formula, we get a volume that's, of course, just a little smaller than Earth's volume. We get 9.3 times 10 to the 26 cubic centimeters.